Hey everybody, this is Professor Monty. We're going to do things a little bit differently today. I've already got everything written down, so we're just going to go a little bit quicker so you don't have to watch me write everything down, and I will just talk through as we go. So as you can see, we've started chapter 13. The first section, of course, 13.1, it's called the chi-square distribution. And chi is written as this like curly looking X you see. So that's chi-square, and it's pronounced chi-square, not chi like the T. So anyway, chi-square is a new distribution that we're doing. I've drawn a picture of the chi-square distribution, and notice it's a right skewed curve. So what we're going to be doing, we're going to be evaluating and calculating a value for chi-squared. And what's going to happen is that chi-squared is going to give us a value similar to how we would get a z value or a t value before. And then the area to the right of that chi-squared is going to be our p-value. So when we do a hypothesis test, we're just going to be doing the hypothesis test just as we were before by using the p-value and comparing it to the significance level alpha. Okay, that's actually all we have in 13.1. So we're going to jump right ahead to 13.2. And 13.2 is called the chi-squared goodness of fit test. So what we're doing here is we're going to do hypothesis testing, and the test is called the chi-squared goodness of fit test. Okay, so you can see what I wrote, looking at multiple possible outcomes and testing against some distribution that's given to us. Okay, so here's what's happening. Think back to when we were looking at proportions last time, and say that we had a proportion before of 60%. And now we're doing a test on a new population to seeing if the new population has a distribution different than the 60%. Well, we were only comparing the distribution of one certain element and looking at that percentage or the proportion in relation to the population. Here what we're doing is we've got multiple possible outcomes. So before we just had one outcome. Now we've got multiple outcomes. So we'll see as we do an example what we talk about in that regard. So notice the null hypothesis for any of these problems are all going to be the same. The distribution is the same as, and the other, let's change that to the given instead of the other. So let's go ahead and change that. We'll say the distribution is same as the given, and we have to fit in distribution here. So whatever they tell us the distribution is. And then the alternative hypothesis is always going to be the distribution is different than the given distribution. And again, we'll see examples of what I'm talking about shortly. Okay, in order to run a hypothesis test, just like z-tests and t-tests, we have certain assumptions that have to be fulfilled in order for us to run the test and for the results to be accurate. So the first one is that all of the expected frequencies are at least one. So if you're doing something and something happens 1% of the time, so 1 out of 100 times, but your sample size is only 50, we wouldn't expect that 1 in 100 to happen in 50 times. Our expected value, our expectation would be that would only happen half of the time. So that would be too small. We'd have to have a bigger sample in order to run it. And then at most 20% of the expected frequencies have to be, well, at most 20% of the expected frequencies can be less than 5. So at least 80% of them have to be 5 or bigger. And then lastly, the third one, it has to be a simple random sample. That we have no control of as participants. When we're looking at the problems they give us, they'll have to tell us whether it's a simple random sample or not. But unless they tell us it's not, then we're going to assume that it is. Okay, now that expected frequencies we were talking about, the formula for it's real simple. It's just n times p. So it's the sample size times the proportion. That's what I was talking about before when I said if something happens 1% of the time, we would multiply that 1% times the 50, and we'd only get 0.5. Our example here. Suppose we have 10 cars. We've been told that 30% of all match the population proportion. And if the population proportion is 30% or 0.3, then we're going to multiply that 0.3 here times the 10, and 10 times 0.3 is 3 cars. And so we know that. I think we usually think that sort of thing. For instance, if I know the probability of getting a heads is 0.5 when I flip a coin, and I flip a coin 20 times, I expect half of those, or 10 times, it to come up heads. That's the exact same formula we're using here. We're just writing it down as a formal formula. Okay, so notice we have an expectation of 3 in this case. Well, remember from what we said before, 3 is okay because it's at least 1, but we can't have too many. We can't have more than 20% of our possible outcomes less than 5. And we've already got 1 that's less than 5 here. So if that's going to be 20%, that's 1 out of 5. So we have to have at least 4 more categories that all have expected values greater than 5 or equal to 5. Okay, so let's go ahead and read a problem, and try not to read the null and alternative hypothesis yet, although we've talked about what it would be, of course. But here's 1326. This is out of the book. It says road rage. The report Controlling Road Rage, a literature review and pilot study, was prepared for the AAA Foundation for Traffic Safety by D. Rathbone and J. Huckabee. The authors discussed the results of a literature review and pilot study on how to prevent aggressive driving and road rage. Road rage is defined as, quote, an incident in which an angry or impatient motorist or passenger intentionally injures or kills another motorist, passenger, or pedestrian, or attempts or threatens to injure or kill another motorist, passenger, or pedestrian. One aspect of the study was to investigate road rage as a function of the day of the week. The following table provides a frequency distribution for the days on which 16 road rage incidents occurred. Since it occurred those days. And notice we had a low of 5 a couple times, at 5% significance level. Do the data provide sufficient evidence to conclude that road rage incidents are more likely to occur on some days than others? So we see from our sample data that they didn't all happen the same number of, we didn't have the same frequency on all the days. But again, the question as always is, could that just be due to sampling error? Or is it because, in fact, road rage happens more often on some days than others? So when we look at the null hypothesis, we have to assume that all the days are equally likely. So the null hypothesis, road rage, is equally likely on all days of the week. And the alternative, road rage, is not equally likely on all days of the week. Now, when we go through and word the alternative the same way they did, that it's more like road rage incidents are more likely to occur on some days than others, but we worded it equivalently. Road rage is not equally likely on all days of the week. I like the way I wrote the alternative hypothesis, just because it's a test and we're just going to do it on the calculator. Now, here's the deal. The TI-83 and TI-84 calculators don't all have this in there. I have a program that was written that can do the chi-squared test on the calculator. Some of the TI-84s do have the capability of doing a Okay, sorry about that. So some do have this ability, some page where I've got, let's see, where am I? Right here. That's not the screen I want you to see. All right, so let me share my screen. And you're not flipping back to there. Hold on just a second. It's about to come up. There we go. Okay, so here's my screen. So we're talking about this road rage problem. And we have the null hypothesis, road rage is equally likely on all days of the week. And the alternative, road rage is not equally likely on all days of the week. So we're doing the chi-squared goodness of fit test. And as I was saying, not all of the calculators have this capability. Some of the TI-84s can do it, some cannot. They don't have it internally written in as one of the statistics tests. I don't think any of the TI-83s have it written in as one of the statistics tests. So what we're going to do is we're going to go ahead and we're going to do it on the computer, since we're all going to be on the computer for the test, and we're going to do it in MyStatLab. So MyStatLab will be available to you during the test. So I would get used to using it right now. That's the only way most of you are going to be able to do it, this test on the exam. Okay, so now they've got this chi-squared value, and I'll show you off to the side if you would like to see, even if you would not like to see. The formula for chi-squared is actually, we take all the expect them to be. So notice that difference right there. If they're equal to each other, if we actually see how many we would expect, for instance, think back to those white cars. If we actually saw 3 white cars and we expected 3 white cars, then this difference would be 0. And so look back at the chi-squared picture that I drew off to the left. That would give me a value here. The bigger that difference is, the bigger the chi-squared value is. So that's going to start moving the value out here. If it moves too far away, that means there's too big of a difference, and we're going to be past whatever that chi-squared number is. So I'm going to erase those. We'll talk about these chi-squared numbers as we get there. But it's not just observed minus expected. It's observed minus expected. And again, they don't want any negatives, so they're going to square it. They're going to divide by E, and they're going to add all those up. So let's see. All right, so when we do this, let's put a little sigma out here. So they add up all those differences divided by what it was expected to be. Okay, and that's going to give us a chi-squared value. The good news is you don't have to calculate any of those. So the computer, MyStatLab, in MyStatLab, the program we're going to use, StatCrunch, is going to calculate that for you. So just as before, when the problems would say, oh, tell me the value of Z, or tell me the value of T, and then tell me the P value, it's going to say, tell me the chi-squared value, and then tell me the P value. Okay, so anyway, we're going to do those tests. You can see I already have the numbers there because I've already written because I've already computed this. But what I'm going to do is I'm going to show you how I computed that. So what I'm doing is I'm taking a picture of the day and the frequency. And then what we're going to do is we're going to go into StatCrunch. I'm going to show you how to use StatCrunch to do this. Now, here's the good part. You're never going to have to enter any of the data into StatCrunch yourself because you'll already have the problem from the computer. I will show you as the next example how we do it once we already have that stuff. But I may be showing you a little bit of stuff here that you don't need to know, but I didn't want to do all your homework problems, so I pulled a problem out of the book. Okay, so let's jump over there. So I'm going to jump into StatCrunch. So let's see, let's go here, and then let's go into the homework. Okay, now off to the left, and again, you'll just be doing this within your homework, but I'm going to click on StatCrunch to pull it up all by itself. And let's see. Now, it talks about down here at the bottom buying StatCrunch, but we can go straight to the website. Again, you don't have to do any of this. And I'm going to open StatCrunch. Okay, so what I'm going to do is I'm going to go up here, and I'm actually going to enter all of our data. So here, bear with me a second. Okay. So now let me do this. I'm going to put in the day here. I didn't put in the day. I'm going to put in the day. I'm going to tab over, and I'm going to put in frequency. And then I'm going to enter all. Now, I'm not going to type all these in, but we'll say Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Okay, so there's our days. And the frequencies, we'll be able to put those in. So we have 5, 5, 11, 12, 5, 5, 11, 12, 11, 18, 7. Let's see, 5, 5, 11, 12, 11, 18, 7. Okay, perfect. So we've got all the data in there. That didn't take long at all. But again, you're not going to have to enter it yourself. It'll already self-populate. And I'll show you that shortly. Okay, super easy to use StatCrunch to do this. You may, in fact, want to use StatCrunch the rest of the semester instead of your calculator because we have it here. So we're going to be doing our tests online. If we had computers in the classroom, I would just be using StatCrunch. I wouldn't be teaching you the calculator in the first place because watch how easy this is. We go into Stat, just like we do on the calculator. We go down to where it says goodness of fit, and we do the goodness of fit chi-squared test. And it says, okay, where's your observed data? So I click here. I say, oh, it's the frequency. And then in this case, the question was, are all of my frequency numbers equally likely? So I click all cells in equal proportion. And that's it. I click compute and I'm done. Well, that was not very hard. Here's my use over here. So let me, I don't even have to write those down. I already have them written down on the other page. So notice it's a 13, oh look, 13.072 and a 0.0419. So I went ahead and I went up to more decimals usually than they ask us on the calculator or on the computer. But that's what I got. Again, here's a picture of what's happening. There's my chi-square value. I listed it here because oftentimes they'll ask us on the computer what it is. My p-value, 0.419, and notice that is less than or equal to the 0.05, which was alpha. I circled that over here. My significance level is 5%, so 0.05. Again, if you need to change those to percentages to make sure it is actually less, go ahead. Clearly 4.19% is less than or equal to 5%. So it's below our standard, so we reject the null hypothesis. Again, this 4.19 is essentially saying that there's only a 4.19% chance the null hypothesis is true. That's lower than our cutoff of 5%, so we reject the null hypothesis. And we answer yes in terms of the question. Yes, it appears road rage occurs more frequently on some days of the week than others. So I kind of shifted it up and worded it the way the question was asked, as opposed to what I put for my alternative hypothesis. But you could have said as well, yes, it appears road rage is not equally likely on all days of the week. Again, those are equivalent. You could do it either way. Okay, so again, notice how similar this is to all the other hypothesis tests we're doing. It's just testing a different thing. Notice it's testing the proportion of multiple things. We've done proportions for a single thing, even with two populations, comparing them, but it was still comparing a single proportion from one population to the proportion of the same variable in the other one. This time we had different variables. Our variables this time were the 7 days of the week. Okay, let's go down from there. We're going to do another problem. And the other problem, notice it's not down here because we're going to go straight in. I'm going to show you on MyStatLab how to do a problem through MyStatLab. So let's flip this around. And what I'm going to do is I'm going to jump into MyStatLab. So let's see. So let's go back into the calculator. I don't need to be here in StatCrunch. Can I go over here? That's still in StatCrunch. Where is, well, everything's in StatCrunch. Oh, there we go. That's where I want to be. So where I want to be is I want to be in the original. This is where we do our homework. So I'm just going to click on homework. And I'm going to go in. And in here, what I'm going to do is I'm going to do chapter 13, problem number 3. So let me show you how this works. And you can see I've already done it, but that's okay. I'll just do a similar problem. Okay, so notice, look, I already have the answers. So let's do a similar question. Okay. So now let's read this one. It says the distribution in the observed frequencies of the values of a variable from a simple random sample. Remember, that's one of our 3 assumptions that have to be true. From a simple random sample of the population provided below, use the chi-squared goodness of fit test to decide at the specified significance level whether the distribution of the variable differs from the given distribution. Okay, so that sentence is essentially our alternative hypothesis. So let's go through, we'll set up our hypotheses. So let's see, let me write on here. We look ready to go. So my null hypothesis, I'll just write it up here so we have more room. The distribution is the same. As the given distribution. Now notice I could just be reading off to the side. My suggestion to make sure you learn how to do these and so you don't make any silly mistakes, do the problem yourself and then look to see what matches your problem. It's very easy to just read answers and say, oh, that one looks good. And you pick it and you're like, oh, of course that was wrong because, and then you think about the reason. So I suggest actually writing everything down. The alternative hypothesis, well, that's what the question says, whether the distribution of there differs. Now, here's the good news. We don't have any left-tailed tests here. We don't have any two-tailed tests because remember, the distribution doesn't go left forever and right forever. It starts at 0 and goes right forever. It's always just, it's essentially a right-tailed test, but it's testing to see if there's that difference, that observed minus the expected. So the alternative is always the distribution. Let's get rid of that big old long line. The distribution differs. From the given distribution. B says the distribution of the variable differs. No, that's an alternative. C says the distribution of the variable is the same. That looks good as the given distribution. And the alternative, the distribution of the variable differs. Well, it's got to be C. Let's see what's wrong with D. Oh, D says the expected frequencies are all equal to 5. Well, that's one of the assumptions, not that they're all equal to 5, but that's definitely not the correct answer. So we'll click there. Well done. Thank you very much. Okay, now it says, oh, what's chi-squared? Oh, so from here, and I'm going to erase the hypotheses, but from here we're just running the test. So let's clear all my drawings. We're going to flip back to StatCrunch, but watch how easy this is. Notice up here, let me get a different color pen, red. Notice up here, there's a little symbol right there. That symbol is what you click on to download all of the data into StatCrunch. So this is what you're going to be doing. So you're going to say, oh, I need to get my data. So I click here and it says, where do you want to open it? You say in StatCrunch. And all my data is already in there. I just have to run the test. So that's why I'm saying StatCrunch is so much easier than the calculator, because we don't even have to enter anything. So we just go stat, goodness of fit, chi-squared test. Now notice this one's different than the last problem. The last problem, we want to know if all the days were equally likely. This time, we're looking at this distribution over here, where the first one would be 20%, the next one 10%, the next one 20%, the next one 30%. So in fact, we want to know if our frequencies over here are actually matching this given distribution. Not all equally likely, because those are all different numbers. Now, we should check that if we multiply these, notice this is P. Well, that's the frequency. It's not N times P. But if we wanted to multiply all these out, N would be the total of all these. So if we added them all up, N, let's see, we have 16 and 18, which is 34, 37, 39, 40, 50. So we have 50 altogether. So if we do, let's say this, let me cross that out. These will be our expected values. So expected N times P. Well, we have some P's of 20%. So we'd go 50 times 0.2. Well, 5 times 2 is 10. And then that 0 moves the decimal. So our expected here would be 10. Oh, okay. That's more than 5, so that one's great. This one's also the same. This one's also the same. If we did 50 times the 0.1, oh, that's 5. Oh, 5's okay. And if we did the 50 times 0.3, we get 15. So these are all E. So this one would be 15. Notice all of the expected values are greater than 1. And in fact, they're all 5 or greater. We don't have 20% that are less than 5. Since we had 5 outcomes here, one of these could have been less than 5 and we'd still be okay, because that would be exactly 20%. You just can't have more than 20% being less than 5. So it meets all 3 of our assumptions. So we're definitely good to go. Okay, so in this case, the observed value, that's what our frequency is. And our expected, it has to match the distribution. And again, we just say compute. So there we have our chi-square value exactly 11. So I'm just looking over here, our chi-square value and our p-value. Chi-square is 11, p is 0.0266. And I wrote that on the other page, so we'll see that when we go back over. But let me clear all this off so it won't stay on our screen. And then we will just switch back to what we're doing here. We're not doing it there. Let's go back. We were doing it all right here, weren't we? That's where I want to be. Okay, so chi-squared. I should have written that down, shouldn't I? Let's see. Seeing if I have it in my notes. I don't see it in my notes. Oh, that's because we regenerated the problem. It's going to be a different problem. So let's go back. I'm going to write these down so that I have them. Okay, so let's see. So chi-squared is exactly 11, and the p-value is 0.0266. All right, now we can answer the question. So now let's go back to our problem. Chi-squared, that was exactly 11. So we'll check that. How about that? The p-value, we got, let's see, it says 3 decimal places, so 0.027, because remember it was 0.0266. 0.027. Check that one. Wow, we got that right also. Okay, so now it's going to ask us to come to the conclusion. Let's write our conclusion down rather than looking at theirs. Again, if you're just looking at theirs and you're getting the right answer, that's fine. But if you're getting some of them wrong, I would suggest writing them down. Okay, so here's what I do. Here's my procedure, the same as it always is. I'm going to say my p-value. Now we had a p-value equal to 2.027. We're comparing that to see if it's less than or equal to alpha, which they said someplace. Oh, here it was, 10%, 0.10. That was my alpha. Oh, I didn't want that big line. That was my alpha. And that is less, because notice that's 2.7% and that's 10%. So move the decimal in each twice. So we say, yes, that is true. So we reject the null hypothesis. And then our conclusion is, yes, it does appear that the distribution of the variable differs. Yes, it appears, and I'll just shorthand it here, the distribution differs. Okay, so we have that. So if I look over to see which one it is, does the data provide sufficient evidence that the distribution of the variable differs? So we're going to say yes, because there is sufficient evidence to reject the null hypothesis. I'm not even going to read the rest. We know it's A, and we're right. Okay, so that's the way we're going to do the goodness of fit chi-square test. So pretty straightforward, just like any of the other hypothesis tests we've done before. We're still just comparing the p-value to alpha and determining whether or not to reject the null hypothesis. So what I'm going to do from here is we're going to jump back over to the problems or the lesson. And what I'm going to do, that's the end of that. Let's go ahead and erase this down here. And we're just going to jump into this last section. And the last section, contingency tables and association. Remember, a contingency table cross-classifies two different variables. We've done this before. Let me write this down. Let's say we did this. That's not what I want. Clear all drawings. Okay, let's get out of there. I want to go back to here. All right, let's see if I'm drawing the right thing again. Oops. Let's try. A contingency table cross-classifies two different variables. We did this, let's say these tables, during probability. So I just have one example here. I just probability. I just have one problem here, and there's only one problem on your homework to do. It takes a while to do because there's so many things to fill in, but let's go ahead and just do one of these. It should look familiar to you. Now, I'm going to erase all this stuff here because we're going to fill it in. Nope, there's more down here. Okay, so the problem says school enrollment. The current population survey from the U.S. Census Bureau provides data on school enrollment. The following contingency table shows school enrollment below post-secondary in thousands by level and gender. So remember, that's what we were talking about. With a contingency table, we cross-classify by two different things. In this case, level and gender. And so what we're going to do is we're going to fill out the table. A says, first of all, how many cells are in the table? Well, the cells, it's what we see outlined in the dark or in the blue now. It's just where the data is. It doesn't include the wording and it doesn't include the totals. So it's just 4 and 4, it's just 8. So how many cells? Oh, there's 8 of them. Fill in the missing entries. Okay, now to fill in the missing entries, what we need to do is the key is looking for either a row or a column that only has, that's not a very good end, that only has one missing value. Okay, the rows go left to right, the columns go up and down, kind of like columns on a building. So look for one that only has one missing value. For instance, if I look right here, this kindergarten number in that first column, that's the only number that's not there. So what I'm going to do is I'm going to take this total, the 29,363, and I'm going to subtract away the other numbers in that column. So I'm going to subtract away the 2331. I'm going to subtract away the 16,504. And I'm going to subtract away the 8393. All right, I'm just going to do that on my calculator real quickly. So 29363 minus 2331 minus 16,504 minus 8393. And I get 2135. So that number, I'm going to erase all that stuff now. That's going to go into that missing spot. So let's see. So let's erase all this. And we get what? 2135. Let me put that in before I erase it. 2135. Okay. Now you can erase that one over there. So now let's go to another one. Notice in the female column, there's 2 missing. So I can't go there yet. But the number I just put in, the 2135, I can add that to the 1997 to get this total value here. And so that's just those 2 added. So it's 2135 plus 1997. And now I can get that one. 2135 plus 1997. 4132. Some of you are probably saying, I was born in 1997. I was not. So we can enter that number, 4,132 here. And now we can do the same with elementary, add those together to get that number, 16,504. Notice we could have done that as my first step if I wanted to. 16,504 plus 15,734, 32,238. Let's plug that in. I have to write a little bit smaller. 32,238, 32,238. Hopefully I can read that because I'm going to need it. All right, let's erase this stuff over here. Now, this number here, I know those 2 numbers have to add up to the 16,446. So I can do 16,446 minus 8393 and get that number. 16,446 minus 8393. And we get 8,053. All right, let's erase some of this. 8,053. Now what I can do is now I can add the females down to get the total. I've already got that 8,053 in there. So to that, I'm going to add 15,734 plus 1,997. Oops, 1,997. That number has to go. And 2,377. So I just add all those up in my calculator. Let's see, I've already got the 8,053, so I just say plus 15,734 plus 1997 plus 2377. And I get 28,161. All right, so 28,161. Now, I can add these two up to get the total, but that also has to be the total of these. So I'm going to do it in both directions, make sure I get the same number both times. So let's see. So let's double check it that way, because if I don't get the same number both times, I made a mistake somewhere. So over here, I'm going to add up the 29,363 plus 28,161. See what I get. Over here, I'm going to add up the 4708, the 4132, the 32,238, and the 16,446. Hopefully these will match. So let's see, I've got the 28,161 in there already, plus 29,363. I get 57,524. And if I add those up, 4708 plus 4132 plus 32,238 plus 16,446, I get 57,524, and they match. So I've got the right answer. So I'm going to put that in. Let's put that in green. That's the grand total. 57,524. All right. So now I can erase all this stuff. We don't need that, but we can answer the rest of the questions. And they'll be quick because we already have the table done. The table was the big thing. Fill in the missing entries. Done. I did. What is the total enrollment? Oh, that's what I got here. That's my 57,524. How many students are female? Well, to find the female, I go into the female column, and then the number at the bottom under total is the total number of females. So 28,161. How many students are in high school? I do a similar thing. This time I go to high school. Let me erase this one so it doesn't confuse you. I go to high school and I look at the total in high school. I didn't want to erase all that. So I go here, and the total in high school was this number right here. So I say, oh, that was 16,446. And then the last question, so let's erase that. The last question says, how many students are male kindergartners? So notice what this one is. They have to be male, so they have to be in this first column, but they also have to be in kindergarten. So if they have to be in this row. And so what I'm doing is I'm just looking to see where those overlap. So the overlap is that 2,135. And I'm done. So anyway, that's the idea of this last section. Again, we've already seen it. This may have all just been review, and hopefully it was, and hopefully you're thinking that was simple. It does take a little time, obviously, because we have to go through and we have to do those calculations. But that's something you definitely can understand and do. And if you don't understand it yet, learn it so you can do it. So anyway, hopefully that was helpful. And that's the end of chapter 13, which is the end of the material for this next test. So bear that in mind. Our next class will answer any questions on chapter 13, and then any previous problems from the homework from chapters 10 or 12. And then the following class meeting, it's just review day. I'll just answer questions on anything throughout any of the 3 chapters. And then the following class day will be the exam. Okay, that's it. Hopefully that helped you out. And as always, remember, stick with this, make sure you do your homework, and you can do this. All right, I will talk to you all later. Have a good day.